Welcome to Biology My Passion. I am Soumya Harikrishna. In the previous videos, we learned up to the series and parallel connections and their implications. Now, we will discuss another effect in this of electricity, that is heating effect of electric current. We know that whenever we are using any gadget, means any appliance, after some time it gets heated. For example, if you are using your laptop for some time, or if you are working your TV for some time, or if you touch the body of the refrigerator, you can see that it is getting heated up. Or mixie, even if you run for maybe 1 to 2 minutes also, it will get heated up. Actually, the work is not meant for that, right? From a mixer, what do we want? Electricity that we are providing is used for rotating the blade for grinding things. But here, lot of energy is lost in the form of heat. The same way, we are switching on the fan. Fan is supposed to rotate and give us the effect. But here our fan is also getting heated up. So in all these cases, heat is getting wasted. But there are certain places where we need electricity or the effect in the form of heat. For example, electric toaster. If I want to toast a bread, I need it to be heated. Electric kettle, where I want to boil water. Or electric oven, where I want to heat or bake. Or electric iron box, where we have to iron the dress or press the dress with a high heat so that all the wrinkles will go off. Or geyser, where I want to heat water. So in all these cases, in which form I want the energy? In the form of heat. So energy is lost in the form of heat, but if we can use it in a different way, we can have benefits out of it, right? Such appliances, the circuit is purely resistive, means high resistance, so that it will produce a lot of heat. This was first explained by a scientist called JOULE'S, and so it is called the Joule's law of heating. Suppose in a circuit there is a resistor. I am not drawing the entire circuit, you know that. Suppose this has resistance R, and through this the current I is flowing for time t. Then according to Joule's law of heating, H is the form of energy we are getting. Here we are getting energy in the form of heat. That heat is directly proportional to the square of the current. So what is the current flowing through the circuit? Its square will be the proportional to the heat. Then heat produced will also be proportional to the resistance. Means if you increase the resistance, heat produced also will increase. And the third factor on which it depends is heat is proportional to time. More time if you work, more heat will be produced. So all these three, if you combine and write, H is equal to I square RT we can take. So this is called a Joule's law of heating. So Joule's law of heating states that if a resistor is there with resistance R, through which a current I ampere is flowing for time t, then the heat produced will be directly proportional to square of the current through the resistor, it directly proportional to the resistance, and also directly proportional to the time in which the current is flowing. Now we have to see the derivation of this. So we know that heat is a form of energy. Energy means power into time. So power means what? Power is actually the work done. Okay. So we already learned one equation in which work done is coming. Do you remember which is that? Yes. V is equal to W upon Q. That is potential difference is equal to work done by Q. In this work done is there. So how will I write work done? Work done is equal to V into Q. So work done into, so we can write that work done per time is power. So VQ is the work done. During a time t, the work is done. So we get the formula VQ by T. Now Q by T is I, current. We learned the first formula, I is equal to Q by T. So we can write VI. Okay. So what is our final equation? Power is equal to potential difference into current I. P is equal to VI. But now we have to find out the energy. Energy means power into time. So power already we found. V and I into T. So we get VIT. According to Ohm's law, what is V? V is equal to IR into IT. So how many I there? 2. So I square RT. So here we are getting energy means it is heat. H is equal to I square RT. I repeat, here we have to find out the derivation of this. So heat is a form of energy. Energy is the power into time. Power means work done during a particular time. So here work done we are taking as VQ. From the potential difference formula we know work done is VQ upon time. Then we know Q by T is I, so we can rewrite the formula as VI. So VI into T is the energy. So VI according to Ohm's law is IR. So I square RT is the formula for heating effect of electric current. Let's now see certain applications of heating effect of electric current. So mainly three applications are mentioned in our NCERT. The first one being heating appliances. Just now I pointed out to you about certain appliances where we need energy in the form of heat. For example, electric iron, electric kettle, geyser, electric oven, not microwave, okay, electric iron, toaster. All these we need energy in the form of heat. So in all these appliances we can use a circuit with a pure resistivity so that we get maximum heat out of them. Second is a bulb. So bulb filament, as I pointed out in the last video, it is made up of a pure metal called a tungsten. So tungsten has got two advantages for considering as a heating filament. One is it has got high resistivity. As a result, the resistance is high so that the current cannot flow easily through it. When the current flows through it, lot of resistance is there. As a result, the filament current is not able to flow through it easily, so heat will be generated. As a result of the heat produced, it will start emitting light. That's what we are getting. But at the same time, the bulb will produce a lot of heat, but we are not experiencing that heat much because inside the bulb there are gases, inert gases filled like argon, nitrogen, etc. Now, what are the characteristics favoring the electric tungsten to be used as an electric filament? First one, tungsten has got high resistivity. Second, tungsten do not burn immediately or oxidize in the presence of high heat. For example, the melting point of tungsten is 3380 degrees Celsius, so it is not melting easily. But if you have looked at the tungsten filament very carefully inside a bulb, you can see that it is very thin, like thin like a hair strand, and it is coiled and kept. So here we can correlate with the factors affecting resistance. We know when length increases, resistance also increases. So when they are making a long coiled filament, the length is increasing, so definitely resistance will be high. And also they are making it as thin as possible, because we know when area is decreased, resistance will increase, right? So that's the second application of heating effect. Though we are getting the energy or output in the form of light, but what are we using? The heating effect. The heat is used to burn the filament to start glowing in the presence of electricity. Then last is fuse. About fuse we have discussed in the magnetism chapter in detail. So fuse is actually something which can prevent the undue flow of electricity, thereby protecting our gadgets or avoid all the hazards associated with the electrical power. Okay, so here what is happening, when the undue current is coming into a circuit, the fuse wire will melt. So we are using a suitable material. Usually tin plated copper is used, not pure copper, so that it will melt easily if the current more than the expected current is flowing through it. Usually fuse ratings are different: 1 ampere, 2 ampere, 3 ampere, 5 ampere, 10 ampere, 13 ampere, 15 ampere. So whenever a current more than this is flowing, it will melt, that is thereby disrupting the circuit, so all our gadgets will be safe. So these are the applications of heating effect of electric current. The last topic of our discussion is electric power. So already we learned what is power. Power means rate of doing work. That is P is equal to W by T. But here we know that the work done means power means what? How much energy is consumed in the household, right? How much energy or electrical energy we are using, that is the power. We are using means the gadget is drawing. So here we can we derive the equation is equal to VQ by T. Q by T is I, so we got the first formula of power, P is equal to VI. So this is the formula to find out power. Power is directly proportional to potential difference of current V and I. Now the second equation we can derive from here. P is equal to, according to Ohm's law, V is equal to IR. If I can write IR into I. So P is equal to I square R. So that is the second equation we can use in this regard. Third, again P is equal to V into I can write V by R according to Ohm's law. So power, third equation is V square by R. So we have three equations for power. One is VI, second is I square R, third is V square by R. Out of these, the suitable equation we have to use to solve the numericals. Now we are learning about something called a commercial unit, because at home we are drawing electrical energy from the potential difference that is given to our homes, and we have to pay for it. For that there is a meter board kept outside. So we have to find out how much power is utilized per time. That is the energy. Energy, we know that it is power into time. Okay, so here we know the unit of power. If I see, the unit of power is watt, and this is volt, this is ampere. So volt into ampere is power. So at home we are using watt as the unit of power, and time we are not taking in second, because no gadget we use for seconds, we use for hours. Suppose a bulb is switched on, we may use it for 3-4 hours, or a fan we may use at night and all 8 hours. Like that, so many hours we use, right? So here it is in the form of hour. So this is the unit of energy, watt hour. But here again at home, watt is actually a small unit for our household. So we use a higher unit, that is called a kilowatt. Kilo means what? Into 1000, right? So watt multiplied by 1000 is kilowatt hour. So this is the commercial unit of what? The power. So if you convert it, 1000 watt is 1 kilowatt, and 60 seconds into 60 minutes is 1 hour. So we know that this is 1000 into 3600. Okay. If I multiply, I'll get 36, 1, 2, 3, 4, 5 zeros. Now I have to take it like 3.6. So 1, 2, 3, 4, 5, 6 I am taking. So 3.6 into how many decimal places are there? 6. 3.6 into 10 to the power of 6 joules is a 1 kilowatt hour. So this is watt second. Here we converted into watt second, and this is joule. Okay, so whenever you are given a problem to calculate the electricity consumed in our household, they will give in watt only, but it is your duty to convert it into kilowatt and then multiply. Hope you understood all these concepts of this chapter very well. I expect your valuable feedback, and all this numerical I will try to do in a different video. Please like, share and subscribe to my channel, Biology My Passion. Thank you for watching.